Great, thanks for having me. Welcome everybody to the first presentation of today. My name is Bartle. I'm a telecom engineer at ClearSpace, and today I'm going to talk about what Jean-Paul already mentioned, is basically how we tackle this problem of increasing amount of space debris, and how that could maybe be a stepping stone into a whole new industry that could enable tons of new services, tons of new companies arising, and talk also a bit about what challenges we face, technological challenges, and yeah, I hope you enjoy. So Jean-Paul already talked about a lot of my first slides here. So how can I do? All right. On this slide, we can see I wanted to show again how much space industry evolved actually over the last years. Some of you know the figures. I'm not going to quote them because I don't know them by heart anyway. But something like 50% of all satellites being launched, ever were launched in the last couple of years. That alone shows already that there's a huge interest in space, a huge boost in all sorts of areas, communication-wise, commercial, defense, and so on. And that leads to basically people just launching satellites into space and nobody really talking about how are we gonna deal with the problem when it's basically too full, too crowded, too dangerous to launch humans into space, which might well be a scenario we're looking at if we continue how we're doing the next 50 years. So we're looking at roughly 3,000-ish satellites in orbit, active in orbit right now, alone. All the Starlink satellites over the last 20 launches or some increased that number by quite a bit. But the bigger part is actually non-functional objects anymore. There's old rocket bodies, old satellites, space debris objects, and so on, that are just there floating around and waiting to deorbit. And this poses a bit of a problem, right? As Jean-Paul mentioned, access to space is getting more and more difficult due to this problem. And also operations, they get more risky. We need to do more maneuvers to avoid colliding with debris and so on. So we need to do something, right? And for this reason, EPFL started early on, back in 2009 or 2012 actually, to think about this problem and how to clean up our footprint that we left in orbit or in space. It started with several projects. Clean Space 1 was one of the first ones, targeted at cleaning up space. Out of this effort that was put into in EPFL, the company ClearSpace was founded, a small startup company, in 2018. And then we bet on different requests for proposals, different projects, and finally in 2020 we got our first big mission, the ClearSpace 1 mission funded by ESA. So I'm not going to go too much into detail on the company because the mission is more interesting, I guess. So let's talk about that. ClearSpace 1. We can see here an artistic depiction of how it's somewhat going to look like. You see here this black thing on the right. I pointed here. This is going to be the target that we're trying to capture. And yeah, it's basically an old part of the Vega C rocket. It's called VESPUP, stands for Vespa Secondary Payload Adapter or something like that. Basically, this ring here, is the adapter for the main payload, and inside of this dome is the secondary payload. It weighs around 100 kilograms and is like 2 by 1 meter in size, made out of carbon fiber composite and aluminum. So yeah, and it was launched in 2013. So by the time we'll try to capture it in 2025, it was in orbit for already 12 years. It was never designed to stay in orbit for that long, or it's not designed for that. So we have no idea on what the actual state of this target is. We know from observations roughly that it still looks something the same, but it might be, instead of black, it might be white or has completely different reflectional properties and so on. And this is a huge challenge for our navigation and camera algorithms and so on. So how are we gonna capture this thing? Basically, it's very easy. You just launch in an orbit. It might not be the same orbit, depending on launcher availability. So we need to do some orbit maneuvers after we commissioned our satellite, do some orbit maneuvers, do some phasing to align the orbital planes. And then once we're in the same orbit, we still have probably a couple 100 kilometers or whatever, a couple of kilometers of distance. And in our case, when we're about like 30 kilometers behind the target, we start switching to a relative navigation. So that means we're now not going to look at our position in inertial coordinates, in absolute coordinates, but relative to the target. And then we do for several stages, we approach the target with different sensors, different measurement devices. And once we're about like 15 meters apart, we start the final approach and then eventually the capture. You can see we have like four phalanges, four arms on the spacecraft that will try to capture it and then secure it. Once it's secured, we then can go on and do an orbit maneuver again. Before that, we need to detumble to some extent, obviously, because there will be some momentum that we exchange. But then we can do an orbit transfer maneuver into an orbit where we will burn up rather quickly. This first mission is designed that the spacecraft that we built will burn up with the target, just to keep the mission timeline shorter. But future missions definitely aim at reusing the services spacecraft several times. So now the question is, how do we tackle such a simple mission? How do we engineer this? And it was decided early on in the company that we want to go for a model-based system engineering approach, in which there's a very close connection between all the information that we have about our system. And we're following a process that is basically looks like this. It's based on the Department of Defense architecture framework. Yes, Department of Defense. And it's a rather simple process when you look at it this way. You have some initial requirements, derive some more requirements a priori, and then you go into an operational domain, say, okay, what do I do? What has my system has to do after each other? What are the different mission phases and so on? And then you look at how you implement these different operational activities with functions that your system has to do. These functions are then organized in a classical functional tree breakdown structure. We do another loop again, maybe, and define some more requirements. And then at some point, we allocate these functions that we identified to physical components, meaning we build our system. So we design our architecture that we want. Here you can see the first the top level operational diagram that we have. Basically the phases that I already mentioned. We have something that happens pre-launch, LEOP commissioning, service orbit raising, phasing, and then all the rest of the mission. Right? In this tool that we use, we can model the transitions, the conditions that need to apply to transition from one period to another, and so on. Here, for example, a functional model of how the phasing looks like. We have a determined service orbit, that's something like a GPS receiver and so on, and we calculate a maneuver. We really go into quite a lot of detail in what we need to do in order to achieve the mission. Yeah, here's this functional tree that we can organize the information and also connect requirements and components to it and so on. And then finally, we end up hopefully with something that looks like this. It's basically a physical tree, like a physical block diagram, where we see the interfaces between our subsystems, the interfaces to the outside world here on the right side, and so on. Yeah, so that's basically it. A rather simple process. It's just that it takes a lot of time, a lot of effort, a lot of thinking and a lot of iterations to do that. And now I kind of want to talk a bit more about the problem that sometimes people are not that much aware of. When people talk about on-orbit servicing, most of what is talked about is the relative navigation and the capture system itself, which obviously are very important parts of the whole thing. With those technologies, the whole mission rises and falls. But from a communication point of view, from what I do at ClearSpace, there are several challenges that are not intuitive, let's say, that need to be tackled properly in order to make this mission successful. So yeah, as mentioned, the spacecraft that we are developing needs to be very agile in how it maneuvers, because depending on how the target is tumbling, we need to maybe be able to capture the target from a different direction. So we need to talk to the satellite regardless of its attitude. Several older or classical satellites have this requirement, but in our case, it is really a safety issue, right? It comes from safety issues. We have to avoid at all costs that we are colliding with the target and potentially generating even more debris. So for this case, we need data rates for commanding and for telemetry. We need to have those available at all attitudes. In addition to that, the amount of data that we need is quite high due to the fact that we need to update algorithms on board. We need to get all the data from the image sensors and all the other sensors that we have on board down, and so on. There's a lot of data that needs to be exchanged, and that makes it quite challenging due to the high data rates requirements. Again, there's a careful trade-off then to be made between data rates and how long our operations are. For this first mission, we sort of have a maximum amount of time that we can take, or that we can take to deorbit this piece of space debris. Everything above that will be quite challenging, or won't satisfy our customer either, basically. So yeah, so either we wait longer for the data, prolong the mission, and with prolonging the mission, we increase the risk of collision and all sorts of things that can happen in orbit. But if we just increase the data rates, our communication system will be more complex. In addition to that, we have several requirements on, again, coming from safety-related matters, on the latency and how long we can be to continuous contact with the ground station with the satellite. It's basically stems from the fact, if you imagine we have our capture of our final approach and capture phase of the mission, it's going to be around 20 to 30 minutes. And during that time, we need to have constant supervision, right? We need to constantly know what's going on. We not necessarily have to intervene. That's something we're looking at the moment, if that's necessary at all. But we want to know what's going on. We want to have some sort of live image feedback, some sort of status information of the navigation filter, and so on. So we need continuous ground station coverage. And if you think about it, a continuous at the orbit that we're looking at, a pass over the ground station is usually like 6 minutes long. So we need to change several ground station passes without too much interruption, which is quite challenging to do. Additionally to that, we sort of, for the whole spacecraft, we have this sort of conflict of interest. We want to be as cheap as possible, because obviously cleaning up space is not something people like to pay a lot of money for. So we want to be as cheap as possible, while on the same time being very, very reliable, right? As I said, we don't want to generate even more debris than actually is already there. That would be quite catastrophic for the company. So there's this constant trade-off on the whole spacecraft system and equipment and component level and so on, of using commercially available low-cost, but not as reliable hardware, and then on the other side having traditional space hardware that comes with a price tag. Again, here distributing risk, we can think about using CubeSat hardware, for example, but then making it more redundant, and that might be still cheaper than buying a high reliable piece of hardware and so on. So that is a very careful trade-off that we need to do throughout the whole system, not just the communication system. Going hand in hand with that, we have the ground system that we have. It's not just the ground station; it's a whole system that we're developing ourselves new for not just this mission, but also all the future missions, to have the capability to launch 20, 30 of these service satellites, and they will all over LEO in low Earth orbit at several places will clean up space, basically. The whole ground infrastructure has to be low cost as well, and in order to make the whole mission cheaper, and therefore the success of the company more likely. Then there's one issue that I find quite interesting, one challenge that we have to solve, or we're not even sure if it's that much of a challenge actually, is that of spacecraft charging. Basically, when you have a traditional docking and berthing maneuver in, for example, at the ISS, these things are very controlled. So you know the potential and you know the charging of the ISS, of your approaching spacecraft. You have several good measures in place and the docking mechanisms and so on in order to deal with this problem. In our case, our capture is non-cooperative. Our docking, basically, I call it docking. It's the capture is non-cooperative. So we don't know in which state the target is. We don't know what charging state it is in, and we don't really know what our charging state then is. And if there's too much of a potential difference, meaning voltage, we could run into problems EMC-wise once we make contact. So we need to deal with this problem inside the capture system, so somehow coat the arms and do proper measures there, but also in the whole EMC design of the spacecraft. Lastly, I have a few slides that are quite interesting. So now I've mentioned that we need to be able to talk with the satellite regardless of its attitude. That is before we capture. After we capture, the situation is a bit different, because we now have this huge chunk of, in our case, carbon fiber and aluminium, so conductive structure in very close vicinity to us, which means basically our antenna pattern will change, and we might not be able to in certain attitudes, we might not be able to talk with the satellite. Especially after the capture, we're probably tumbling, as I mentioned. There's going to be an exchange of momentum. Then therefore we might have intermittent links. So this is something that has to be analyzed and simulated properly, carefully. Here, for example, is the ED-orbit study that ESA did a couple of years ago. Some of you might know, especially the space debris experts, this huge thing here. This is MBSE. It's an environmental, I think, weather satellite. It has this huge SAR antenna here, a huge solar array. The whole thing is about the size of a school bus, weighs 6 tons, and so on. So it's huge. It's among the biggest and most dangerous pieces of space debris in orbit that we know of. In this study, they looked at what happens when you have to settle the service spacecraft here, this thing. What happens to the antenna pattern, and how can we still communicate it after we capture it once this huge metal structure is in the vicinity of the satellite? They simulated the radiation characteristic, the antenna pattern of the spacecraft, and it looks something like this. I'm not going to go into too much detail here. I could go on for hours, but basically the gist of it is the red part is good. In the red part we have a good link. In the green and blue part, not so much. These are just due to the antenna configuration here that we don't have good link here. It's just installing antennas on a spacecraft that's how it looks like. But then once you capture the satellite, the whole thing looks a bit different, right? This is simulated in a simulation software. But as you can see, you have huge parts now, huge areas where you're not going to be able to talk with the satellite. You have this area here, this blue horizontal bar. This is the SAR antenna. Up here is the spacecraft body itself. And all the way up here, this is the solar array. And now if you're tumbling and basically your coverage went from, let's say, 80, 90% down to 60%. When you're tumbling, you have to account for that. Yeah. So these are some of the challenges that we're facing. I hope we can solve them. I'm confident we can solve all of them. And, yeah, I hope this mission, I'm very confident this mission is going to be successful, and we open up a new kind of business, a new kind of market with this kind of technology. So yeah, thanks for listening. Here's my contact information. If you have more questions than we can answer today, but yeah, thank you all.
Thank you very much, Hannes. So I'll just be reading a few of the questions. So what is the plan if for some reason your spacecraft fails before you catch the target? How could you mitigate the fact of having 2 dead spacecraft instead of 1? First question.
Short answer, through proper design. Longer answer, basically, I mean, these things can happen, right? I mean, there's reports of satellites, you launch it into space, and then there's a single event upset and your electronics fries. So that's barely preventable. But we take every measure, as I said, through careful trade-off, careful selection of high reliable components that we know they won't fail, but as I mentioned, they come with a specific price tag, and trade that off against these lower cost components. So that's basically what we do. There's also, I mean, we do launch in a 700-kilometer orbit, or we launch into a 500-kilometer orbit. The target is then around 700 kilometers. So if something happens before we reach the target orbit, then we're basically deorbiting in a couple of years. So that's not a major issue. Once we're up there, then we're looking at 25 years plus, or 50 years, or even a decade, and so on. So that might be worth it.
Okay. Now, second question: what kind of propulsion do you use?
Basically, it's not yet fully decided. We started last year. We are in basically phase A, B, now phase B kind of status. But it's definitely going to be some kind of monopropellant or bipropellant solution with several reaction thrusters and maybe a main thruster. Yeah.
Okay.
I can't really go in. Unfortunately, I can't go into really specifics because a lot of it is proprietary. But yeah.
Okay. Next question: do you require agreements or contracts with various countries for ground station requirements? How can you ensure access to required frequencies to run your operations?
Basically, the process is very similar to just a normal satellite mission. We file for frequencies at the ITU for the bands that we need, which is going to be S-band and maybe X-band, and then we have a radar system which needs a filing. And then basically everything else will be done, or all the ground station licenses will be done by a ground station provider. So we're looking at there's several providers out there. There's KSAT, there's SES, no, SSC. Wait, I don't remember the name. But there's several networks of ground stations, and then you can select which ground station locations you want. If it's going to be Svalbard or Inuvik or something on the southern hemisphere, and they do all the work for you in terms of frequency allocation or ground station license. Frequency allocation we have to do ourselves.
Okay. Do you hope to achieve reusability for such a servicing spacecraft?
Definitely. With this first mission, it's not a main goal. we do have some requirements that are looking, well, basically with the future in mind and reusability in mind. But since the constraint on this first mission, which is an ESA mission, is are a bit different, we don't have as much freedom in designing the spacecraft as we want to, or as the a reusable service would require. Let's put it that way. But definitely, yeah, reusability is a big issue.